Thanks for coming. This is the second talk about an example which I try to explain. I try to explain a very concrete example for which I call non-reductive integration formula. Was explained by Francis before, and also I give a reminder today, and also gave a reminder yesterday. So it's going to be an integration formula for intersection numbers on non-reductive quotients, and in this particular case, the example is moduli of jet. So let me start with a reminder. So the starting point was the space which we look at is maps from C to Cn germs. So the zero means these are map germs. And there is a group acting on this. This is what we call the diffeomorphism group, K. So we take the space F sits in K1n, which is the set of germs with from C to Cn, and phi, an element of this group, actually acts on this space. This is an affine space. The group diff K is using this notation is JK11, so it's a polynomial reparametrizations of C at the origin, and we take the regular part, which means that we take those jets with a non-zero linear term. And so the action is phi acts on F, so it's going to be a new germ, so it's going to be F compose phi. And I remember that this was really a non-reductive group action, so in this basis which you have, or a risk scale basis if you want, is given by a K by K matrix, which I was also sometimes by just U hat is some matrix group where you have parameters on the first row, and there is a one-dimensional C star, diagonal C star, and some polynomial entries in these parameters. So, and that's a group, right? And so the goal here is, I motivated this yesterday, that we call the the set of apps up to this reparametrization group. This is the set is what we call the moduli of jets, which is a quasi-projective object. And there are different compactifications of that, and we are particularly interested in this non-reductive GRT quotient, which is a compactification of this quotient. This is a smooth projective space, and we are interested in. So I denote this by xk. We are interested in. So the goal today is to explain the elements of an integral formula on xk of the, let's say, so some churn, in fact, any churn number of this bundle. Let's say this is a dimension k times n minus 1 of dimension k times n minus 1, and we'd like to explain a formula for this. It's going to be an iterated W formula. Right. Okay, so in some sense, it's going to be a little bit boring because I really want to go through the details of this, identify the elements of this formula, which let me put it down here, right? Because it's yeah, anyway, I will come back to this, the formula. So let's see the setup. So you have this. So we have this U hat. I mean, I was not precise here, not precise enough here. So it's going to be some projectivization of this. I can call it in this way, but the right setup is that we always start with the projective space. So U hat acts on, and now this is actually we take the trivial compactification, so C plus JK1M, and just introduce coordinates on that, because as I said, this is going to be a very concrete. So coordinates are, okay, let's say just the F prime, F double prime, F to the K power. So these are coordinates, these are the coordinates there. So the Fi's are all in Cn. And so the action is, so you have to take an element U hat times, so we extend this action to this projective space. It extends, so if you have X and M, it's going to be just, it's going to be, actually, this is a left action, so it's going to be X and M, U hat, M times U hat inverse. So this is a matrix. You see, it's kind of, it doesn't do anything. It's it really acts on the affine chart. And then that's done. That's the most trivial thing we can do. So the question is, can we find a grading one parameter subgroup for this? So the grading one parameter subgroup is going to be, so lambda t is equal to, if you look at this group, we have to find something in the reductive part. It's just a C star. So it's not too much to do. Actually, we can shift this C star with the center element. So what we do is actually just take the, you have to be a little bit careful here. So this is a left action acting on the inverse. So it's going to be the T inverse to the minus 2, T to the minus K. So that means that okay, let's put it in. So we use this grading one parameter subgroup for many things, but it's kind of one thing immediately we can find is the minimal weight space for the action. So does that mean it corresponds to the first column? Sorry, it corresponds to there's only one weight, which has 0 weight. So there's only one coordinate with 0 weights. So it's going to be just the point. But the stabilizer of, so it's like it's a point, right? So and let's say this is, yeah, but the stabilizer of in U hat of this point is, you see, I mean, there's nothing changes, so it's going to be the full U. Oh, sorry, the U stabilizer. Right? So this point is not changed by U. U acts on this, the other coordinates. So far, so good. Yeah. And then, so that's not good. It's not the stable, semi-stability with stability condition. We have to get rid of this U here. So on Z-min, and it's, it's a very lucky situation that it's enough to take the one blow up, which is just a trivial blow up. So this, we take blow up. So this is my notation today. P tilde is the blow up of at this point 1, 0 of P. And that's P. And that's so let's put it down. So that's going to be What is that? So it's going to be x, let's say v1. I just use v1. Vk. And the w1, wk, such that wi tensor vj is equal to wj tensor vi. So that sits in p to the kn times p, and it's kn minus 1. This kn minus 1 is really just the normal bundle of this. So it's got a tangent space. So it's p of the tangent space of at t0 of jk 1n. Can identify this, the tangent space at that point is just really just the tangent space at the origin of the affine space jk1 is the projectivized space, and that's the exception divisor. So let's see what happens with z min, right? So that's the you'll see that. By the way, we have to pick a linearization on the blown up. So whenever you have a blow up, you have to take, you pick the linearization. And the linearization is, we will make a well-adapted shift of this, but we start with L, which is just the, so yeah, so P of K and 1. And so, right? And so let's see the stabilizer. So Z min theta. So what is that? Well, that always corresponds to the smallest non-zero weight. The next weight, actually, this is 0 weight. And the next weight is going to be 1, corresponding to those coordinates, which have n of those, corresponding to the first column of this matrix M, right? So Z min theta is really, well, if you want to put it down, it's just really the point 1, 0, 0, sorry. W1, 0, 0. So these pairs, and W1 is in Cn, of course, and the point is that W1 is non-zero. So that sits in the exception divisor. Exception divisor is P of E0, K1M. And we'll identify this as the one. So the point is that these coordinates are 0 because this is the minimal wave space in the normal direction, in the tangent direction at that point. And so, and we have trivial U stabilizers. So why is that? Because the action on Z min theta is really just you can see it from the action on the affine space JK1M, and it's really just the thing is that if this, so if you look at this as a matrix and it's a matrix multiplication, what does it do? It acts constant times lower, so lower derivatives to higher derivatives. So if f prime is non-zero, then you can see that in order to get, since f prime is non-zero, so in order to get the things will be stabilized and not change if and only if all of these alpha 2 up to alpha k are 0. So we have a trivial stabilizer. Alpha 1 can be, because it's a projective space. So up to scalar, this is a trivial U stabilizer. So the issue here is not the blow up. It's not getting to the stable into equal semi-stable case. And that's a really lucky situation because in most applications of this theory, of course, this is the hard part of the theory. So once you're in the situation that you can apply this moment map and integration formula, in order to get there, you really have to first achieve a semi-stability, and the blow-up construction is it's a little bit more involved than, well, I wouldn't say more involved that, but it's equally complicated as in the reductive case. But as I said, here it's not the issue. This is really this is why it's a nice example. So in one step you get there. Okay. So now what we want to do is the following. So in general, we want to do so. In this, we want the integral of the formula for over xk of kappa u hat xk, or yeah, I will just say, you can put it here. So P tilde mod U hat, that's the GIT quotient, right? So we can now form the trivial U stabilizer. So, oh, by the way, yeah, so trivial U stabilizers. So I'll just finish this. So we have a P tilde mod U hat. And this is an L minus. So we have it's a smooth projective quotient for a well-adapted But before we get to the well-adapted shift, I really want to put down the formula because it involves an integration over the Z min tilde. As you see, the Z min tilde now is really a projective space. And as I mentioned yesterday, so there will be a second classical reductive integral formula or Jeffrey current formula, which we use, is just really on the projective space on the Z min. So we have an extra weight. So we work with equivariant in equivariant cohomology. One weight will come from this C star, that's going to be the Z weight coming from the C star in U hat. The other weight will come from the fact that this is really a quotient by a C star, and that's the other weight. That's going to be a W weight. So I'm just saying in advance that we have two weights, Z and W. These are the residue variables. One Z corresponds to the U hat C star, and the other one is for the Z min tilde, which is the projective space. So we get there in a second, but let's put down the formula itself. So we have if you have an I will explain this in a second. So you have some homology, rational homology plus here that will come from the surjective curve map. So eta will actually be an equivariant homology element on P tilde. And then, but it's not necessary on P tilde. I will explain in a second. So we have Z min. So we have some constant times, and then you take the residue at Z or 0 of, we only have one variable here, so Z of the integral over Z min of just the usual terms here. So it's the restriction of your equivariant form to the minimal weight space. So because this is an equivariant form, so it has an equivariant parameter Z that represents the generator, or in degree 2 of the equivariant cohomology ring, C star equivariant cohomology ring of Z of the affine space in some sense, because it's a code so that represents the we talk about C star equivariant cohomology rings. It's just really just the coming from the equivariant the polynomial part of the cohomology ring, the equivariant cohomology ring, the C star equivariant cohomology ring. And then we divide this by the equivariant Euler class of the normal bundle of Z mean. But they also multiply the order class of what I denoted by VU. So this is really just the product of the weights of the grading C star on U. That's also polynomial in Z. Everything is as in now polynomial in Z. Right. So this is the formula we would like to use in a special case because we want to compute this integral here. Sorry? Yeah. And that's the right-hand side. Yes, I will explain now. Yeah, just a second. Yeah, so I explain. So what is this here? This is the left-hand side is a cohomology, a rational cohomology form on this quotient, which comes from an equivariant form eta under the Taylor map, which I put down now. So there's an, what is it? Yeah, because it's surjective, so you can always get it as a, in other words, eta is an equivariant extension of this form, a C-star equivariant extension. Let me put it down, because that's anyway, I have to do this. Because it's a very, it's a really delicate issue. So where does this come from and where is it defined and so on. So there, so okay, just delete this. So there we have the following. So you have the so we have the homology of this. So my x is just going to be this. X is here, P tilde, if you want. So x mod u hat is a rational homology. This is, as I said, this is a smooth projectivity, so it's well defined. And so that's the surjective. There's a surjective map from. So originally we have this from the U hat equivariant cohomology ring of X, but that's the same as the S1 equivariant ring or C star equivariant ring. I think I just say C star of X because it's a deformation retraction, so the cohomology ring is the same. But then there are these. Yeah, exactly. So you see that the group is really just retracts to the diagonal system. But there's these two surjective maps. So one is really to the semi-stable part, but you can actually take X min, the space X min, and the same U has equivariant cohomology ring of that, and that's the same again as the S1 cohomology ring of X min. Yeah, sorry. So these two surjective maps, either of these or the composition you can call kappa if you want. So, but it's kind of a delicate point because some of these forms. So we have this form, and then this is your eta here, which you like to work with in this case, the first rank class of the tautological bundle, and that's what it should be. This is equal to, sorry, so you have this eta here, and then kappa eta is 0, right? So kappa u hat. It's kind of just this usual game. Then for equivariant localization, we instead of working with the ordinary form, we have to take an equivariant extension. But for bundles, it's just really taking the line bundle here, and then this line bundle really comes from an equivariant bundle up there, and that's the same equivariant class of that gives you the lift. So It's just a reminder saying that this is a residue variable. Z stands for so Z is H star C star, or let's say lambda C star, because there's this one point, the subgroup of the point is S dot or whatever, if you want, a Q of Z, right? Yeah. Single residue, same reason that center of U hat is just again right. Yeah, exactly. So this number of so you know the number of residue variables is just the rank of the group, rank of the reductive part of the group. So it's work in general, like for any, not just for U hat, but for any non-reductive group where you have a central, where you have a reductive part. And that has some, for instance, for a parabolic, you have the Levy, and the Levy has high dimensional maximum torus. So there you might see. Then you have a high dimensional, like a iterated residue. But it also depends on what your minimum weight space is, right? So it's really. But yeah, sorry, for the second part. But for this one, it's really for this Z. This is really the. Sorry, for that Z actually, So for U hat quotient, it's only one. It's always just one variable, right? And then if you take another group which has a high dimensional, then you can perform a second quotient by the residual action of the reductive group modulo this lambda C star, and that you can apply again the integral formula. So then you have an iterated residue of the right size. But it's a two-step process, even that. And this is a different two-step process because then, or in that case, there is a first step. The first step is really looking at what the minimum weight space is, and in most situations, it's some sort of homogeneous space, and then you can also iterate it as an iterated residue, so that's fine. Yeah, and that's a very good question. So. So it could come from any of those. So there's a surjective map. So there's an extension, but you only and that's the point, is that because so we know that X mean contains I think so in our situation is I should have maybe just I really want to let's change back to P tilde because then it's well, no, it's fine. X over U. So X mean in our situation is it actually contains Z mean. It's always true. So it's not just in this special case, but it's always true that the minimum weight space is contained in Z X mean. So and then you see in the formula we only work with in the Z mean. So it's enough to actually know the restriction of this equivariant form on X mean, or in particular it's enough to know the restriction to Z mean. So we don't really have a full knowledge about this extension. We just have to know what's the restriction to this Z mean or restriction to X mean, which is much. Yeah. Okay. So yeah, let's put this here. So you have an isomorphism from H S1 of the K tilde 1n. So this is and then this is equal to H S1 of the exceptional divisor Q. So let me explain this. So we know that X, so X is equal to P tilde in this picture. X mean is equal to that's JK tilde is equal to the blow up. So JK tilde is equal to the blow up at the origin of JK 1n. And the exception is contained the exception divisor, which you already and so this is really just the projectivization of T0 JK1. So it's really just because we want to work with we will just restrict your equivariant form to the Z mean, which contains in E. We really want to understand the weights, the equivariant cohomology ring of this space here, which is like it's just a simple project because you know the weights of the action there. And why this is true? Because E retracts to because action retracts to E equivalently. So really working with the upshot here is that although we have a form here, we really want to work in the S1 equivariant cohomology ring of the exception divisor. Remember that this is actually contains a Z mean here. Okay, so I will come back to this. So we see that so eta, we can assume that eta is an element of H S1 is H S1 of the projectivized tangent space of the jet of JK1N. And so that's really just because this is so what we see that we can think of this as so this and so we can think of this as just, if you want, T0 JK1N. This is just T0 JK mod C star with a W weight. So this is not precise here, but you can make it precise. So this is really just, you can put either a projective geometric quotient with a C star, but the weight is W. This is what we use. So in other words, the equivariant cohomology ring of this is really just a polynomial in one variable, and this variable is W because it's an affine space, right? So this is equal to, this is really just the Q of Z. So we have two weights now. So so the point is that I go on with the discussion. So so these two C stars, so gamma C star, and so let's say just C star Z and C star W. These are commuting actions on T0 JK1M. So let's see the weights of this. So the T, so let's say this is, we can also say T2 is the product of these two. We don't even have to introduce this. So but these weights for this action on this tangent space, on this tangent space, well, it's really just, you see, let's go back to the original picture. We have this, we have the, what's the CZ, so C star weights on this. But on the, we have to weight on X, that's a trivial action. And the weight on the first column is 1. It's a right, actually, you have to take the inverse. So it's 1, 2, up to K. So the weights are, on this space are Z, 2Z, up to k times z for the C star, so the Z weights. And for the W weights, what is the W? W is just really a rescaling with equal weights. So that's going to be just plus W. Right? So these are the weights. All with multiplicity n, right? So we have this space is really is the same as a JK1 and as a so set of matrices. The first column is as this way, second and the kth column. Okay. I identify the weights, these on the that, and then once we identify the weights, we can work out the shift of the value adapted shift. Now, the value adapted shift is really for the W weight is not really matters for the value adapted shift. So the value adapted shift actually is really just with regarding for the grading one parameter subgroup. But you see the weight we have to really shift to make this weight. This is the minimum weight for that Z to be minus epsilon times Z. So there is a shift which you have to perform such that the first weight becomes negative and the other weights positive. So what we have is a shift where so it's going to be L minus. It's going to be the shift of L. So it's going to be some sort of it's going to be O and A. Yeah. And so O e to the, or in other words, O e of 1. That's a rational shift. And such that the minimal weight is such that the weights of L minus on the same T0 JK1N, they become, instead of that, they become W minus epsilon Z. And then, of course, then it's going to be W plus 1 minus epsilon times Z, and so on. So it's just a central shift, right? So we have to shift all of the weights with the same multiple of Z. So now we have this value adapted shift. It's very important to make this comment here. So for the first of all, the localization data of the formula, so the denominator, and also this one here, this will not depend on the shift. The only thing which depends is, of course, the restriction of the intersection number, which we actually look at. That's what it depends on. That this part, not this part, not does not depend on that. So and also the quotient, it will not depend. The quotient will be the same for any choice of rational epsilon, and in fact, we have to take a sufficiently divisible multiple of L minus to make it an integral shift. So it doesn't really matter. It's only changes the result up to constant, which is also the same in the reductive world. So yeah, exactly. So for sufficiently ample n, what we have is the following. So we have, on one hand, we have so the C1 of, now we really want to focus on that form, which is just coming from the bundle. So O of what U hat of 1 is coming from an equivariant bundle, which is a sufficiently ample multiple of that. So it's kappa u hat. So the image of under this surjective, its equivariant extension is equal to L minus to the n. This is your shift. This is what you use to construct the GIT quotient, but you need this sufficiently ample power to make it integral first. N is your capital N. It's just, because this is normally like a rational shift. You really, on one hand, you want to work with integral weights. So in other words, you want to, and it's just, and it's just, sorry. Sorry, I'm sorry, that's what yes. It's sufficient divisible, I'm sorry, that's an integer. Sorry. So this becomes sufficiently ample. Anyway, and the other thing is that if you want, we can identify this as admin tilde. As I said, the exception divisor is the quotient of this is the projectivized tangent to JK, and Z mean is just that part of this where the weight is minimal. So it's just really just going to be that part of JK 1n. I put it here where the weights, the original Z weight is Z plus W, so that's the minimal weight. So it's going to be just the first column in the matrix representation, and that's divided by C star V. And so all we really matters here is that, so the C1 of the OZ min tilde 1, which is going to be the normal of the exception divisor in the blown up space. It's going to be, so it's, in other words, this is the Euler class of that normal direction. This is going to be the kappa u of L minus to the n restricted to this space JK and Z plus W. And then I'm kind of, the point is that this is with weight. And so this is what we will put in here. The restriction is n times Z minus the shifted weight. So Z W minus epsilon Z. All right. So, because that's the weight here. So this is a notation for the minimum weight space, but then of course we shifted the weights to W minus epsilon. Right, so that's the, at least, so we identified this part of the formula because that's really independent of anything else. We just come to this one. Now what is left is identifying the tangent direction equivariantly. So, and for that, we really, what is that? So we have to identify the normal bundle of Z min tilde. Z min tilde is a projective subspace of the exception divisor. So this normal bundle in the blown up space is going to be two components. One is the normal bundle in the exception divisor, and the other one is this normal direction in the which is the normal of the exception divisor in the blown up space. So if you put this down, these two, then we are done. So let's do that. But before we do that, Actually, we can do that now, yeah. So let's identify the others and then we can, yes, so I want to leave the formula here. So the next step is, what is Euler class of VU? This is the equivariant Euler class. This I just put it down. So what we just take the product of the weights of the C star action on the Lie algebra of U, and that's, you see that from the matrix, which is not there anymore, but from the matrix representation, we have alpha 1 to alpha 1 to the k. Sorry, we had the grading one parameter subgroup. So if you take what is the Lie algebra is the basis for the Lie algebra is really just this parameterized on the first row. So we have to check what are the weights of this diagonal C star on the first row under the adjoint action. It's going to be, if the ith place, you're going to be the weight in the ith place in the diagonal minus the weight of the first place in the diagonal. So the weights are really just 1 to up to k minus 1. So this is really just 1 times z times, actually it's minus z times minus 2z times minus k minus 1 z. So it's going to be minus 1 to the k minus 1 times z to the k minus 1. That was easy. And then, sorry? This is just my notation from yesterday. Was so VU is really just the bundle over the symplectic portion. So mu hat inverse 0 cross S1 of L of it's kind of the Lie algebra of mu. So U is the Lie algebra of U. So it's just a Lie of U. So there's a C star weights on the Lie algebra, and that's really just the associated bundle over the portion. Oh yeah, it's kind of important. Yes, thank you. It's still not good. Yeah. So I will erase this. Oh no, I just put it here. So the Euler class is really just identifying the normal directions, and that's again just the game. So the last step, or one of the last steps, is the Euler class, the equivariant Euler class, and this is now of the normal bundle of the minimal weight space in the blown up. So this has two directions. Is equal to the Euler class of n. Well, let's say just put it down in this way. So z mean tilde sitting in E times the Euler class of E sitting in T tilde. So this is equal to, for this first one, we have to identify the weights. For that, they are going to be, again, so this is the subspace corresponding to the weights. Did I erase the weights for, yeah, that's here. So this weights. And the other weights in the exception divisors are these. So really the weights are the differences. So we just put it down. Yes, so these are just, so what's are the weights? So it's going to be Z times Z to the, how many of those? We have N of those, Z to the N times 2Z to the N times K minus times N. So this, you know, the differences between these, K minus times Z to the N. And this one here is, this is why we put it in this way, that it's really the quotient, but in this, the normal direction has weight Z plus V, so it's going to be Z plus W, W plus Z. There's a dual issue here, so it's going to be, this one is minus Z actually, but it doesn't really matter, so it's a constant maybe. Okay, so so what we have here is that I think everything is yes, and now we just have to put together the formula. But as I said, there's 2 steps. So we have the integration over the Z min theta, which is a second. So this is the classical Gergely residue formula for C star. But now with respect to W, so what we have is okay, so we integrate over P tilde mod U hat the form C1 of O P tilde mod U hat of 1 to the right power, so K times N minus 1. Okay. And this is equal to some constant times integral over Z min tilde of the residue at Z equals 0, or we can put it actually out, of this integral, which is C1 of L minus, this is where you take the shifted one to the N Z times the Euler class of VU. Yeah, that's the point, is that actually a dual here. So that's why it's a minuses, but anyway, yeah. So, and here is the Euler class, Euler of N Z min tilde of Z. But so far everything is based on just Z. So if you just put in this way, this is the only one equivariant parameter, which is Z. When you perform the second one, you want to take this integral as a residue with respect to another variable, which is W. So this one here, so we would like to put this as another residue. So it's going to be so let's say it's just N C star, another constant times the residue with respect to the W parameter in 0 of now you take C1, so it's going to be the equivariant class there, times the Euler class of VU over the Euler class of N Z min tilde as here, Z, but now we have to also multiply by the Euler class of the normal bundle. So what do we do here actually? So in order to get that for the second residue formula, we have to think about this So Z mean theta is equal to the T0 JK1N to the weight, to the part where the weight is Z plus W divided by C star. So the weights, and then this is just really the Euler class of this space at the origin. So the Euler class of T0 of JK1N and the weight Z plus W part of that. So it's a little bit complicated way to say that this is equal to here. This is equal to the product of the weights. And since all the weights are the same Z plus W, this is going to be just Z plus W to the N. So if you put down, we put together everything, then we get the final formula. So, and this is now and I will not have time for the jet bundle version of this. So what we get is really just an iterated residue. So this is equal in the end. So we have some constant, which is now depends on U hat and C star, and a double residue W equals 0. And then we have to put N times W plus N epsilon. Sorry. I'm sorry, I have to put the original one. So N W minus N epsilon. So N times W minus epsilon. Is that because it's the, as I said, this is the weight of that, right? So we have the shifted weight. This is L minus. And the weight of this is the minimum weight, which is just W minus epsilon Z times, and the rest is just, we just copy there. So that's going to be, the Euler class is K minus 1 factorial times Z to the K minus 1 divided by this other Z power, which was just K minus 1 to the N times Z to the N times W plus Z. And we have the rest is just Z plus W to the N. And that's it. So we have some cancellation here, but it's actually it's going to be N W, so D Z D W. So yeah, you can cancel it. So it's going to be some Z power down. So and it's not Z to the. It's going to be Z to the, I'm sorry, this is going to be K minus 1 factorial times Z to the and K times N. So that's the formula, and this is the affine version of the formula. And maybe just finish this talk. I would like to mention that there is the fibered version. So the really interesting thing how you actually translate into the integral over JK X mod U hat of some sort of formula which involves this first-term class. And for that, you have a similar picture, but you have to do this fiber-wise, and you can identify the weights and the tangent direction with the parent roots of your original X, which is your manifold. So the way how you use this and the similar way you use this to get the intersection number on the jet bundle on X, not on C and now, but on any X, and that's actually important in the hypervelocity questions. Is that really you do exactly the same, but then in the end you have some sort of Chern-Weim type map which identifies some of the weights with the Chern roots of your original max. So that's kind of the story, and maybe yeah, and yeah, I think just stop here. So again, so the for yeah, here. What do you mean by that? Yeah. Yeah. Zi minus Zg minus Zk. Yeah. Well, that's because that's not. Yes, that's a good question. So they do not appear directly because those are Thom polynomials are intersection numbers over the curve inner component of the Hilbert scheme, but not over the GIT quotient. And that would be really nice if they were, then we would have a closed formula for them. But as I mean, yesterday I explained, and there is some sort of a resolution of so there's a rational map from the GIT quotient to the curve inner Hilbert scheme. And in order to define, if you want to use this technique, you can always try to resolve the indeterminacy locus of that rational map. And that works. So that strategy works. And that's how you get like the proper localization formula on the curve in the Hilbert scheme.
So is it an improvement of this?
Yes. Absolutely, yeah. Yes. And in some sense, it's an improvement because it was not clear how to resolve this issue with this Borel orbit in the original model. So, and here everything is toric. And yeah. But you certainly, for the Thom polynomial, you have to work with the tautological. It's a tautological intersection number on the Hilbert scheme. And the tautological, you can't see that bundle here. So in other words, you want to have a resolution of this model so that you can pull back this tautological bundle. The tautological bundle is kind of the enumerative geometry part of that. That's why the Hilbert scheme is so important in enumerative geometry, because there's this bundle over that. So if you know any other model where this bundle can be pulled back, then you would be like in a great situation. And in this intersection theory is nice. But there is no way you can see that bundle over this non-reductive GIT model. Yeah. But the intersection theory is nice, and if you understand the map, then you can pull back everything and integrate over that. And that's what happened in that formula. No.